Parallax is a displacement or difference in the apparent position of an object viewed along two different lines of sight and is measured by the angle or half angle of inclination between those two lines. Due to foreshortening, nearby objects show a larger parallax than farther objects, so parallax can be used to determine distances. To measure large distances, such as the distance of a planet or a star from Earth, astronomers use the principle of parallax. Here, the term parallax is the semi-angle of inclination between two sightlines to the star, as observed when Earth is on opposite sides of the Sun in its orbit. These distances form the lowest rung of what is called the cosmic distance ladder, the first in a succession of methods by which astronomers determine the distances to celestial objects, serving as a basis for other distance measurements in astronomy, forming the higher rungs of the ladder. Parallax also affects optical instruments such as rifle scopes, binoculars, microscopes, and twin-lens reflex cameras that view objects from slightly different angles. Many animals, along with humans, have two eyes with overlapping visual fields that use parallax to gain depth perception. This process is known as stereopsis. In computer vision, the effect is used for computer stereo vision, and there is a device called a parallax rangefinder that uses it to find the range, and in some variations also altitude to a target. A simple, everyday example of parallax can be seen in the dashboards of motor vehicles that use a needle-style mechanical speedometer. When viewed from directly in front, the speed may show exactly 60, but when viewed from the passenger seat, the needle may appear to show a slightly different speed due to the angle of viewing combined with the displacement of the needle from the plane of the numerical dial. Stellar parallax motion from annual parallax. Half the apex angle is the parallax angle. Parallax is an angle subtended by a line on a point. In the upper diagram, the Earth in its orbit sweeps the parallax angle subtended on the Sun. The lower diagram shows an equal angle swept by the Sun in a geostatic model. A similar diagram can be drawn for a star, except that the angle of parallax would be minuscule. The most important fundamental distance measurements in astronomy come from trigonometric parallax, as applied in the stellar parallax method. As the Earth orbits the Sun, the position of nearby stars will appear to shift slightly against the more distant background. These shifts are angles in an isosceles triangle, with $2 the distance between the extreme positions of Earth's orbit around the Sun, making the base leg of the triangle and the distance to the star being the long equal-length legs. The amount of shift is quite small, even for the nearest stars, measuring 1 arcsecond for an object at 1 parsecs distance, 3.26 light-years, and thereafter decreasing in angular amount as the distance increases. Astronomers usually express distances in units of parsecs. Parallax arcseconds, light-years, are used in popular media. Because parallax becomes smaller for a greater stellar distance, useful distances can be measured only for stars which are near enough to have a parallax larger than a few times the precision of the measurement. In the 1990s, for example, the Hipparcos mission obtained parallaxes for over 100,000 stars with a precision of about a millisecond, providing useful distances for stars out to a few hundred parsecs. The Hubble Space Telescope's Wide Field Camera 3 has the potential to provide a precision of 20 to 40 microarcseconds, enabling reliable distance measurements up to 5,000 parsecs, 16,000 ly, for small numbers of stars. The Gaia space mission provided similarly accurate distances to most stars brighter than 15th magnitude. Distances can be measured within 10% as far as the galactic center, about 30,000 light-years away. Stars have a velocity relative to the Sun that causes proper motion, transverse across the sky, and radial velocity, motion toward or away from the Sun. The former is determined by plotting the changing position of the stars over many years, while the latter comes from measuring the Doppler shift of the star's spectrum caused by motion along the line of sight. For a group of stars with the same spectral class and a similar magnitude range, a mean parallax can be derived from statistical analysis of the proper motions relative to their radial velocities. This statistical parallax method is useful for measuring the distances of bright stars beyond 50 parsecs and giant variable stars, including Cepheids and the RR Lyrae variables. Parallax measurements may be an important clue to understanding three of the universe's most elusive components: dark matter, dark energy, and neutrinos. Hubble Space Telescope precision stellar distance measurement has been extended 10 times further into the Milky Way. The motion of the Sun through space provides a longer baseline that will increase the accuracy of parallax measurements, known as secular parallax. For stars in the Milky Way disk, This corresponds to a mean baseline of $4 per year, while for halo stars the baseline is $40 per year. After several decades, the baseline can be orders of magnitude greater than the Earth-Sun baseline used for traditional parallax. However, secular parallax introduces a higher level of uncertainty because the relative velocity of observed stars is an additional unknown. When applied to samples of multiple stars, the uncertainty can be reduced. The uncertainty is inversely proportional to the square root of the sample size. Moving cluster parallax is a technique where the motions of individual stars in a nearby star cluster can be used to find the distance to the cluster. Only open clusters are near enough for this technique to be useful. In particular, the distance obtained for the Hyades has historically been an important step in the distance ladder. Other individual objects can have fundamental distance estimates made for them under special circumstances. If the expansion of a gas cloud, like a supernova remnant or planetary nebula, can be observed over time, then an expansion parallax distance to that cloud can be estimated. Those measurements, however, suffer from uncertainties in the deviation of the object from sphericity. Binary stars, which are both visual and spectroscopic binaries, also can have their distance estimated by similar means, and don't suffer from the above geometric uncertainty. The common characteristic to these methods is that a measurement of angular motion is combined with a measurement of the absolute velocity, usually obtained via the Doppler effect. The distance estimate comes from computing how far the object must be to make its observed absolute velocity appear with the observed angular motion. Expansion parallaxes in particular can give fundamental distance estimates for objects that are very far, because supernova ejecta have large expansion velocities and large sizes compared to stars. Further, they can be observed with radio interferometers, which can measure very small angular motions. These combine to provide fundamental distance estimates to supernovae in other galaxies. Though valuable, such cases are quite rare, so they serve as important consistency checks on the distance ladder rather than workhorse steps by themselves. Metrology. The correct line of sight needs to be used to avoid parallax error. Measurements made by viewing the position of some marker relative to something to be measured are subject to parallax error if the marker is some distance away from the object of measurement and not viewed from the correct position. For example, if measuring the distance between two ticks on a line with a ruler marked on its top surface, the thickness of the ruler will separate its markings from the ticks. If viewed from a position not exactly perpendicular to the ruler, the apparent position will shift and the reading will be less accurate than the ruler is capable of. A similar error occurs when reading the position of a pointer against a scale in an instrument such as an analog multimeter. To help the user avoid this problem, the scale is sometimes printed above a narrow strip of mirror, and the user's eye is positioned so that the pointer obscures its reflection, guaranteeing that the user's line of sight is perpendicular to the mirror and therefore to the scale. The same effect alters the speed read on a car's speedometer by a driver in front of it and a passenger off to the side. Values read from a graticule, not in actual contact with the display on an oscilloscope, etc.